Alright guys, my name is Nicholas Miller. I will also be doing the lead for our group on the bomb calorimeter. Alright, and now the first topics I'd like to touch on are all the background thermo, just in case y'all forgot, and some of the units that go into some of the properties that we're going to find here. Alright, the first one is our heat capacity, and you can do a constant volume or a constant pressure value. They're measured in kilojoules over kilogram times Kelvin, and then that is equal to the heat required to raise the temperature of material. Normally it's per unit mass per unit energy. Alright, and the next value is the calorie fuel value, and that was what Alexander was talking about, how many calories can be produced by combusting some certain type of material. So that's basically how much heat you can get out of it. You can find that on like food labels and the calorie count and whatnot. It's kind of the same thing as an example. And then the latent heat of vaporization is the heat absorbed per unit mass for a phase change. So boiling, evaporation. Alright, here's the general theory behind the equation that we're going to use. So the goal of our whole experiment is to find the thermal capacitance, the bomb calorimeter, which we did with our estimates as a lead, and then from that we can find the heat of combustion of these other samples that we want to know. So anything we want to put in the bomb calorimeter, we can figure out how much heat it's going to produce. And we can use the change in temperature, and we can use the water outside since we know how many, that's a known value. We can calculate the Q for that and therefore back out our MCV or just CV values. So those are the two different manipulations of it. It's really simple math for that part. All right, and here's our equipment. This is the big view of it all. I have all the different lump numbers labeled and whatnot. We've got the igniter. We've got our stainless steel bomb that is the center part, number 2, right here. Then we're going to connect we're going to need a laptop for our data acquisition with a lab view. Then we're going to need an analog to digital converter for our values of temperature. So we have thermocouple up there. And we're also going to need the stir with the stir motor, like Bradley was saying, to keep your temperature gradient at a minimum, kind of pull everything out. All right, here's our zoomed in view. All right, we're going to need inlet check valve. We're going to need a pressure relief valve because we are going to be pressurizing this to promote our combustion. And we're going to need some electrodes because those are going to plug into our sample so we can ignite it. We're going to need a crucible that's going to hold our actual sample, and we're going to need to attach the wires to it. All right, and now here's our procedure. Just summarized all the steps a little bit for everybody to see. We'll prep it up. We'll load the fuel cell into the crucible, connect up the ignition wires, we put 1 milliliter of water in there, and then we remove the air by pressurizing and depressurizing it. Process. All right, then we'll fill up this water jacket out here with 2 kilograms of water, kind of make sure that we have enough water to see a change in temperature, but not too much that it's not noticeable. All right, then we'll drop the bomb into the bucket of water, set the stir motor, and then for the exact experiment, we're going to log room temperature for about 2 minutes, I believe, so we have a good plateau of data. And then we'll ignite the fuel sample, and we'll stop the data acquisition once we hit that plateau at the top, like we saw in Alexander's raw data. Depressurize the bomb, turn off the stir, and then we can actually measure the length of the unburned wire from the igniter. And there's a special calorie scale that depends on, shows you how much heat was put in. So based on the measurement and how much of it was burned and whatnot, you can actually tell the energy input. All right, and this is my beautiful handwriting for the calculations because I just wanted everybody to see that. All right, so first thing you do is you're going to take your Q equals MCV delta T, and what we did, we approximated the system as 2 kilograms of water and then 3 kilograms of steel. I actually used a median value between the two steel values for 4. And this was a median value. I found just normal steel, and then we found stainless steel as well. But I just took a median because it doesn't specify in the lab handout when we're calculating it. So we know the CV of water is 4.186, and then we use both of them together for our system, factor out the delta T, and we actually bring that to the bottom over here. And so we can find our MCV value, which I found about 9.8 kilojoule per Kelvin. And then for the benzoic acid, I found that I used our molar mass because the value that I found of the heat of combustion was in moles. So then I took the molar mass, took a 1 gram sample, divided it, and found in moles, so we can cancel that out. Then I found this value of Q for 1 gram. And then I plugged that into our Q equation down here, and use the heat capacity that we found up here, the 9.8, so we could back out a temperature, and actually found almost very, very close to what the actual experiment did yet again. And I have my sites for the different values and things that I found. Wanted to touch on a couple things for the sources of air. The temperature of water needs to be within 5 degrees of the room temperature, so if you have a discrepancy in your starting temperature, then the heat absorbed and whatnot will be different, because your heat calculation is very dependent on your temperature change. That's what the whole equation is based on. Also, place of your thermocouple is very important, like we did with our first experiment, measuring the ice. If it's touching anything that's not supposed to, it'll change the medium through which the heat transfer occurs. So you want to make sure that's in the water, not touching anything else. And also you need to take your plateau data prior to the ignition, so you can really have a good baseline for everything. All right, and that's about it for me. Does anybody have any questions?
Do you, like, I know other groups have been like bringing in little things to try and like calculate like unknown substances. Are you gonna try and do one? And if you are, what is it bringing?
Well, I was planning on stealing a gusher from one of our friends, because that was a really cool experiment, but I don't know, I might do an icebreaker. Let's always have those on hand, so.
I've been curious about one of those sugar-free gummy bears.
Hey.
They wreak havoc on you inside. I'm curious.
Yeah, we gotta remember to do that. That'd be cool. Anybody else? All right, guys.